Hey guys, BuildZoid here, and today we're going to be taking a look at another X870 motherboard. This time it's the ASUS Strix X870i gaming Wi-Fi. The board was sent over by ASUS, so big thank you to them for providing one for testing. And before we get into this, a quick disclaimer. This is not a review, and I am not an engineer. In the interest of trying to make these videos shorter, I will not be talking about anything I personally don't find interesting. So if you want to know about the connectivity of this board, you're going to have to go read the motherboard manual, because I will not be going over that. Also, if you'd like to support the channel, there are links in the description that you could check out, and that would be much appreciated. And with that out of the way, let's get into it. Starting off with the clear CMOS button, which is recessed into the rear I/O, which is cool, because that basically stops you from pressing it accidentally. But what's not so cool is that the clear CMOS button on this motherboard requires that you unplug the power supply in order for it to actually clear the CMOS. And the main issue with this is on a lot of power supplies, especially high power supplies, the bulk capacitors hold charge forever. So the actual fastest way to clear the CMOS on this motherboard is to unplug the 24 pin and then press the clear CMOS button. Now, ASUS isn't the only motherboard manufacturer to have a bunch of AM5 motherboards with this clear CMOS behavior, but I do find it incredibly disappointing because this board is really rather expensive, and there are plenty of other ITX motherboards out there where you can just press the clear CMOS button and it just clears the CMOS, because those motherboards have a transistor to disconnect the 5-volt standby rail, and this doesn't. So, yeah, I do find that very frustrating, especially because this board is quite good at memory overclocking, and if you're doing a lot of memory overclocking, there's a decent chance you're going to be clearing the CMOS a lot. So that, like, the whole unplugging the 24 pin to get the BIOS to clear gets really old really fast. Yeah, so that is one thing that just, like, to me, that's probably the biggest disappointment about this entire motherboard, is that clear CMOS button. Next to that, we have BIOS flashback, which just allows you to update the BIOS of the motherboard without having a compatible CPU. But the, in my opinion, neater thing about this is that you can also use it for, like, forcing BIOS downgrades, and sometimes it can also recover from corrupted BIOSes. So, yeah, and that isn't recessed into the rear I/O because you have to, like, press and hold that intentionally to get it to actually do anything. So it's not a, you know, like an accidental push hazard like the clear CMOS button is. So anyway, that's the rear, that's the buttons that I care about in the rear I/O. Then we have a fan for cooling the chipset and the M.2 SSDs. I'm sure somebody's going to be like, oh, the fins are not oriented in the direction of the airflow. The X870 chipset doesn't produce that much heat. The fan just agitating the air in the vicinity of the chipset heatsink is more than sufficient as far as I'm concerned. In fact, I kind of suspect that the fan is really more about cooling the M.2 SSDs than it is about the chipset. So yeah, because this is actually kind of a substantial chipset heatsink that we've got here. Anyway, moving on, we have a daughter board for a bunch of our front panel connections. And one thing I like about this is that this does use USB Type-C ports for attaching to the board, which makes for a really rigid connection, like very solid. I really like it. Also, it's not a very cheap way of doing this because USB-C ports are, as far as I know, one of the most expensive connectors that you can get, at least for, like, basic, like, out of, like, the common basic connectors that exist. Yeah, but there are, like, out of the various ways of attaching daughter boards, this is definitely the most solid one, and I do appreciate that. Anyway, we have a CPU overvoltage jumper on here, which basically removes a bunch of voltage limits on the motherboard. I've not found a reason to use that yet, because, yeah, for ambient overclocking, the voltage limits that the board has on by default are perfectly acceptable. There's really no reason, yeah, like this is more for, like, LN2 overclocking than anything on ambient. Then we have this 3-position switch, which allows you to set the, like, PCIe speed. So by default, the motherboard is obviously Gen 5, but if you have, like, a riser that doesn't work at Gen 4 speeds or something, you can actually use this switch to set the board to Gen 3 or Gen 4 permanently. or like as long as the switch is in that position. So even if you clear the CMOS, you still have whatever PCIe speed restriction it is that you need for your system to function. And then if you're wondering about the silver Sharpie over here, I added that because, yeah, it was hard for me to remember which 2 pins on this are the power button. So that was my workaround for that. I kind of wish that, like, at this point, I don't think anybody does it, but Gigabyte at one point was doing, like, color-coded front panel headers. I really liked those. I wish this came with that. Anyway, another little detail that I noticed and kind of appreciate about this board is that ASUS is gluing the fan cables into the connectors, and that's for the fans for the VRM heatsink as well as the chipset, well, M.2/chipset cooling. And basically what that does is if you pull on these cables, you're not going to rip them out of the connector. So that's a nice little touch. And that kind of, nope, that doesn't quite cover it, because we've also got this one LED over here, as this does not have a postcode and it doesn't have a full set of LEDs directly on the board itself. There are troubleshooting LEDs on the Strix Hive 2 USB hub thing. Yeah, I guess that's the best way to describe it. So that has like a full set of color-coded LEDs. I don't know why they didn't put a postcode on it. It's huge. Like, it has space for a postcode. But, yeah, I've not actually had to, like, I've not bothered to plug the Strix Hive in yet when using this board, because this LED lights up when you don't have any memory sticks installed, which is, in my opinion, completely unnecessary functionality. But more importantly, it also lights up when the motherboard is going through memory training, which is very useful, because then you can tell if it's actually going to post or not. Though I'm kind of surprised that we haven't seen an ITX board at this point that just has a single RGB LED for indicating the entire post sequence, right? Because like ASUS like color codes their boot up LEDs. Like you could just have one RGB LED cycle through all of the boot up colors. If like it's a space constraints thing. Anyway, that basically covers it in terms of random like overclocking convenience features. So now let's move on to the power delivery, starting off with the single 8-pin power connector, which for some reason has a metal jacket around it. I actually do not understand what purpose that is supposed to serve, but more importantly, the 8-pin does use solid metal pins, so this is the high current variant of the connector, and one of these will handle a overclocked 9950X with absolutely no issues whatsoever. So, yeah, like, basically, my point here is that if you're thinking, like, oh, it's an ITX board with one 8-pin, it's going to be, like, bad for overclocking a 95. Like, it's going to have a disadvantage against ATX boards with 2 8-pins. Yeah, no, it won't. That's actually not a concern. So, the 9950X is not a 14900K. It's not going to pull 400 watts. Well, I guess if you're on liquid nitrogen, then it might. But even then, like, the 8-pin isn't going to be the, like... Well, the thing with LN2 overclocking is that you're generally running short benchmarks, and in that scenario, the 8-pin is still not going to be a problem. So anyway, the 24-pin, on the other hand, uses folded metal pins for the entire thing, and I actually have no issue with this, and honestly, I kind of appreciate it, because like I mentioned earlier, the fastest way to clear CMOS on this motherboard is to unplug the 24-pin and then press the clear CMOS button. The folded metal pins have more play to them, so the 24-pin is a lot less hard to plug, like, it's less hard to unplug and plug in the 24-pin compared to 24-pin power connectors that use all solid pins, which can get very, very snug, and then really annoying to unplug. So, yeah, and this being an ITX board, you're just not going to be able to plug in enough devices into this thing to significantly stress the capabilities of the 24-pin connector. So using the standard current pins, in my opinion, is not a problem. So anyway, that's our power connectors. Now let's move on to the actual voltage regulators. Starting off with the main part of the CPU's power delivery. Like, technically, this thing over here is also powering the CPU, but we'll get to that. Anyway, so this phase down here is, of course, VDD MISC. I should probably not put that there. Then all of this above that is V-core. And then over here we have our two VSOC phases. And you will notice that the SOC phases do not have a heatsink on them. With a CPU, that is not a concern. With an APU, it might be a problem, but I haven't tested that. Though, there's not really a lot of heat-generating components around the two SOC phases, so they might be fine with just dissipating all of the heat through the PCB, even with the APU, but yeah, that's not something I've checked for. And it really, like, yeah, I guess it could be an issue, but I mean, I don't know why you'd want to stick an 8700G into a $400 motherboard. Anyway, for the V-core VRM cooling, we have this heatsink assembly. This also deals with cooling the 40 gig USB chip over here. And we do have a fan for that. And yeah, that's sort of like on ITX boards, I don't have a problem with having a fan on the VRM because you generally just can't fit enough like surface air. Like there's just not enough space to design a really like good passive heatsink. So getting some extra help from a fan, I think, is a reasonable design choice. I am not a fan of ATX motherboards with VRM fans. That, I think, is really silly. Anyway, let's talk about the VRM controller. So for SoC and V-core, we've got this chip right over here, which is a ASP2205, and that should be a rebranded Infineon controller. And here, so I don't know what Infineon controller it is, but yeah, this is one thing that really annoys me with a lot of ASUS boards, is how ASUS just insists on using rebranded parts and then parts that don't have public documentation because they're special order for ASUS, which I guess is kind of like rebranded parts as well. Because if there's special order for ASUS, how do you know that it's not just a different part with a special ASUS part number? It probably is. But anyway, the ASP2205 here is running in a 10+2 phase configuration, which I found really surprising. I was really expecting this to be a 5-phase with 2 power stages per phase, but nah, it's actually 10 phases. There are 10 current sensing inputs to the controller. There's 10 V-core ones and there's 2 SoC ones. So, yeah, I was really surprised to find that because, yeah, I was really expecting this to be a 5-phase. But it's not like, that's more of like an ASUS thing that it would have been a 5-phase because Infineon does make VRM controllers that go all the way up to like 16 phases. So it's not really like the fact that an Infineon controller can do 10+2, not surprising. The fact that it's configured that way on an ASUS motherboard is surprising. So anyway, that's our controller. And then for our power stages, we've got Vishay SIC 850s. And I recently made a very long video about why I don't like these. And I still don't. So these are supposedly 110 amp power stages. And the problem I have with calling these 110 amp smart power stages is that the efficiency curve for their closest like part, because again, these are special order for ASUS, so there's no public documentation, is the SIC 840. The SIC 840 is nominally a 100 amp smart power stage, but the efficiency curve for the SIC 840 looks like this. And for a 9000 series Ryzen CPU, we're interested in this part of the curve, so that's the blue line. And I have 2 complaints. One, this is a 10-phase V-core VRM. And the peak of the efficiency curve for these power stages is between 20 and 30 amps output, which basically means that the only way this VRM is ever going to be operating in the peak of that efficiency curve is if you're like pushing a 9950X to its absolute limits, because the stock current limit for a 9950X, as far as I know, is 170 amps. So, like, right here on the efficiency curve. And of course, if you use a CPU with anything less, like fewer cores than that, or just lower power consumption than that, the VRM is going to be operating in this part of the efficiency curve. So that's one thing, is just like the peak of the efficiency curve. And this is the 100 amp power stage, right? If the SIC 850 has the same, so there's also an SIC 820 from Vishay, which is a 90 amp part. And the main difference between the 820 and the 840 is that the 820 has the peak of the efficiency curve moved a little bit towards the lower current end of things. So if the 850 follows the relationship of the 820 to the 840, the 850 is going to have that efficiency peak even more towards 30 amps than 20 amps. Yeah, I am not convinced that these power stages are actually the optimal power stage for this VRM. I really strongly believe that ASUS went for these just so that they could slap a bigger number into their marketing materials. Because as like the fact that the efficiency curve also tops out so low is probably a measurement methodology difference between Vishay and the various other power stage suppliers. But the fact that the peak of the efficiency curve is so late in the output current range, I think like there's 70 and 90 amp parts from like Monolithic Power Systems, Texas Instruments, Infineon, Fairchild Semiconductor, and actually at this point that's not Fairchild, is On Semiconductor. So On Semiconductor, like there are 70 to 90 amp parts from a whole bunch of other manufacturers, which I am pretty sure would actually deliver better efficiency in the expected operating range for this VRM. I could be wrong about that. Maybe ASUS has some like internal testing that they've conducted, but I would bet that they actually just wanted a bigger number on the marketing slides. Which, like, to be fair, it doesn't really matter that they opted for a power stage that, like, you're never going to even reach the peak of the efficiency curve on this board, because ultimately it is perfectly capable of powering any CPU that you stick into the socket. But I do wonder if this board wouldn't actually be better with some lower rated parts that have a higher peak efficiency. So yeah, and that's my main issue with the SIC 850s. Anyway, let's talk about the sort of theoretical, VRM heat output numbers. This is based on the SIC 840 datasheet because, again, I can't get any documentation for the 850s. And based on the 840s, 1.2 volts output voltage, 600 kilohertz switching frequency, which is a bit high. Most motherboards these days default to 500 kilohertz. I haven't actually checked if this is defaulted to 500 kilohertz. It probably is. Also, I should point out with modern motherboards, especially with high-end digital controllers like from Infineon, Monolithic Power Systems, Renesas, running really high switching frequencies generally doesn't give you any voltage regulation benefits and just massively increases the heat output of the power stages. So there's really no reason to run, to like raise the switching frequency. Anyway, so 1.2 volts, 600 kilohertz, 200 amps output. This VRM will probably produce about 22 watts of heat, which, yeah, with this kind of heatsink assembly is not going to be any problem to dissipate. And this is also basically, like, this is already more current than a stock 9950X will ever pull. So this is like overclocked 9950X territory. So yeah, this board really won't struggle with powering anything that you can put into the socket. But I think there's power stages out there that could do, like, a 10 phase of some other power stages could do 200 amps at lower heat outputs than this. At least on paper, it seems to be that way. Yeah, and I'm not a fan of the SIC 850s as a consequence of that. Anyway, for 300 amps output, this will probably produce about 34 watts of heat, and 400 amps output, so this is like LN2 overclocking territory. At which point the VRM cooling actually kind of doesn't matter that much because you don't run any load for that long on LN2, which is like your peak current is very high, but you only run it for like a few minutes at most. So, you know, it takes a while for things to heat up. Especially when, like, depending on how you're running the LN2 setup, the board might be actually very cold. Anyway, 400 amps output, about 50 watts of heat. So, is this technically overkill for any CPU that you can put into the socket? Yes. Is it ideal? I don't think so. You know, I haven't been able to test it, but I really do wonder if, like, there isn't a better power stage for this VRM from an efficiency perspective. Anyway, also I forgot to mention that smart power stages are called smart power stages because they integrate a whole bunch of monitoring and safety features, the main ones being built-in current monitoring, built-in temperature monitoring, over temperature protection, over current protection. So, yeah, like, the thing about the overcurrent protection and the over temperature protection is you can technically, like, the motherboard vendor can choose to disable those or just set them so high that they're not really relevant. Which is actually what I mainly suspect about that 110 amp nominal rating is I think this is a special variant of the SIC840 that has a extended overcurrent protection rather than an extended current handling capability. Because in certain scenarios, you might get like a very, during load start, you might get like a very high peak current due to the initial load insertion transient. Actually, no, you won't. And not on this motherboard, not with this platform. Yeah. Anyway, though I mentioned the built-in temperature monitoring and the like current monitoring, unfortunately, you don't get access to any of that because this is an ASUS motherboard, and ASUS basically goes out of their way to block access to the VRM controller. So, like, the VRM controller knows exactly what temperature the VRM is at. It knows it depends kind of on the accuracy of the power stages themselves. The current monitoring isn't like 100% accurate, but it can get very accurate depending on the power stage and implementation of the VRM. But like, so theoretically, this does have some very accurate, like this could have some very accurate current monitoring data that you can't access because this is an ASUS motherboard. And I do just find that like a frustration with a lot of ASUS boards because ASRock, MSI, Gigabyte, whenever they use, not every time, but a lot of the time when they use high-end digital controllers, one of the cool benefits that you get from that is in monitoring software like Hardware Info, you can just see the core voltage and the output current and the operating temperature of the power stages from the VRM controller. Now, the VRM controller won't tell you the operating temperature of every single power stage at the same time because from a VRM controller's perspective, it doesn't actually care. It just wants to know which one is hottest. Yeah, like that's a lot of cool monitoring functionality that you just don't get on ASUS motherboards unless ASUS adds it in extra circuitry that this board obviously doesn't have because it's not a crosshair. Also, they broke the voltage monitor, like they broke the SVI3 TFN sensor. If you do static voltage, like if you try to set static voltages on this board, it breaks the SVI TFN sensor, which I've seen that behavior on like low-end Gigabyte AM4 motherboards, and it's really annoying there, and I can't believe that ASUS somehow managed to replicate it on a high-end AM5 board. I'm even more annoyed about it here because like this thing is expensive, and as soon as you try to set like static core voltages, which for certain overclocking scenarios is just a thing that you do, your core voltage monitoring in Windows is just like it's just gone. The only voltage sensor that is still working is the Super I/O, and the Super I/O voltage sensor is terrible because it measures from the back of the CPU socket, so the voltage reading is always way too high, and this is just like, I don't know why ASUS makes their boards more, like, there are certain extra things that ASUS does that I appreciate, and then there are certain extra things like blocking access to the VRM controller that I really dislike. So, yeah. Anyway, as far as powering the CPU goes, though, it'll do a fine job of that. Now, the SoC VRM just uses more of the SIC850 power stages. And again, if you look at that efficiency curve, so for the vCore VRM, like if you're pushing a 9950X to its limits, you might be able to run somewhere in this part of the efficiency curve. If you're if you're running, say, so 1-to-1 mode and you're pushing, 1-to-1 mode to its limits and 1.3 volt SOC kind of stuff, yeah, that SOC VRM is going to be running somewhere in like this area. And if you're in like 2-to-1 mode and you're like, because in 2-to-1 mode, you don't need a lot of SOC voltage, you might be running, well, somewhere down there. So, yeah, these power stages are like, for the vCore VRM, it might be debatable as to whether or not there are better parts for the vCore VRM from an efficiency perspective. For the SOC VRM, I am like 99% convinced that these are just not the right part for the job if your number one goal is minimizing SOC VRM temperatures. Because you are never, ever going to be outputting, well, with the APUs, you might actually pull a decent amount of current. But with the CPUs, the SOC power supply only needs to output like 10 to 20 amps. Which, like, and that's across 2 power stages. Right? So you're literally going to be operating between like 5 amps down here. So that's like just in the worst, just, yeah. No, these power stages are just grossly oversized for the SOC VRM. Really wish that, ASUS wouldn't, like the vCore VRM, fine, you can have your 110 amp smart power stages, but the SOC, like, come on. Anyway, so, yeah. But again, like, it's not gonna, like, even though the efficiency is gonna be absolutely horrendous, because you're gonna be, running the power stage at, like 5% of its output capacity, the overall heat output isn't going to be high enough to actually overheat them. But it's just like you could have used something a bit more appropriately sized. Anyway, so that's our SOC VRM. For VDD MISC, we have another massively oversized power stage, which is completely unnecessary. This is a Vishay SIC 629, again with no public documentation, because another special order. I'm not sure these are actually special order, but yeah, it's just no public documentation again. Now, ASUS advertises these as being 80 amps. I really strongly suspect that this is a special version of some 50 or 60 amp parts from Vishay. Either way, it doesn't matter, because VDD MISC has to output even less current than the SOC power rail does. And so consequently, there are AM5 motherboards that use like a 35 amp all-in-one buck converter chip, where it has the control, like all of the control circuitry, the driver, both of the MOSFETs, everything is just one chip. This is so unnecessary, especially on an ITX where space is at a premium. So we've got a, full-size basically full-size DR MOS component. Like, technically the smart power stages are bigger because they're like rectangular, but most of the DR MOS components that you will see on like GPUs and stuff are actually this I think it's 5 by 5 millimeters square. Or it's 4.5 by 4.5, something like that. Anyway, so that's like a power stage that you'd see in the vCore VRM of an RTX 4070 or a 4090, depending on which 4090 you're looking at. And then we have an entire separate voltage controller for it. That's even bigger than the DR MOS component. And of course, this voltage controller with enough pins to probably run a 4-phase is running in 1-phase mode. On ATX boards, I just assume that the manufacturers got like a really good deal on these RT3672 VRM controllers, and that's why like this is this setup of like this giant voltage controller and one DR MOS is very common on ATX boards. I'm assuming this chip is just really cheap, and that's why it's so common. But on an ITX, where like this thing is crammed there's no space, like there's barely any empty PCB space. And then it's like, yeah, so instead of using a integrated buck converter, which there are like plenty of AM5 motherboards that do that, it doesn't cause any issues. VDD MISC is not a high power rail. We're going to use this and a separate DRMOS component, which just like very, very unnecessary. Technically very overkill. That doesn't necessarily. It's not really good though. This is not really it's not a positive overkill. This is just like, oh yeah, well, I guess that's that. Now then, moving on to something that I have significantly less complaints about, the capacitor configuration, which ASUS, like I'd say ASUS motherboards probably generally have my favorite capacitor configurations, because ASUS likes to go a bit extra on them, and this motherboard is no different. We have some extra multi-layer ceramics hanging out right over here. But we're going to start with the input filtering. This is output filtering, by the way. So for input filtering, we have a whole bunch of SP caps from Panasonic. These are 56 microfarads, 16 volts. And there is 8 of those in total. So we have 7 on the front of the board. So that's these, this one over here. And then there's also one more on the back right there. And then, because that wasn't quite enough bulk capacitance, which should be fair, like by ASUS standards, yeah, I agree. This is not enough. We also have 2 270 microfarad through-hole aluminum polymers. And one interesting thing about these SP caps is that they actually have a thermal pad on them to sink them into the VRM heatsink. And now, capacitors are not really a heat-generating component. Like, technically, they do produce some heat due to the ripple current flowing through them, but compared to the power stages, they are not a heat-generating component. So I'm assuming the idea behind having a thermal pad on these is basically to try pull some of the heat out of the, through the out of the power stages through the capacitors. Because, yeah, the capacitors themselves really shouldn't be producing enough heat to need heat sinking. Anyway, the 2 through-hole polymers don't have a thermal pad on them because they're cylindrical and that. Well, I've seen some GPUs where they put a thermal pad even on the through-hole capacitors, but yeah, that's really weird in my opinion. That doesn't, I don't think they're even that thermally conductive, so I don't think that actually achieves anything. Anyway, so that's 2 270 microfarad 16-volt capacitors. These are rated for 5,000 hours at 105 degrees Celsius. I suspect they are made by APAC, which is a Taiwanese capacitor manufacturer that ASUS just uses on basically everything except the Crosshair and Maximus boards. Now, I'm not 100% certain that this is APAC because APAC usually has a logo that on their capacitors that is very recognizable. These don't have that. But this is ASUS, so they could, I suspect these are a custom order part from ASUS again, for ASUS again. So, yeah, in terms of the input filtering, I'd say pretty typical stuff for an ASUS motherboard. Not, well, depends, for an ATX board, a lot of input capacitance. For an ATX board, depends on whose ATX board you're comparing against. ASUS, a lot of the time, will just have 8 of these. Well, 6 to 8 through-hole polymers. So, yeah, which in total is a bit more than what you get out of 8 560 microfarad SP caps. But honestly, I've always found the input filtering from a especially for CPU power delivery, is really not that important. So, yeah, I don't really see any, I don't have any complaints for that. Now, actually, the better way to put it is, I'm not really that interested in the input filtering on this board. However, the output filtering for VCore, I am a big fan, because it's these. And these are 470 microfarad, 2.5 volt, 3-terminal Panasonic SP caps. And these things are basically the best aluminum polymer capacitor that you can get for output filtering. Now, what do I mean by 3-terminal SP caps? I mean, you see these, well, you can see that they have these little legs coming out the sides. Those are a third ground pad. And it looks like that. And the reason that pad exists is because regular SP caps already have an equivalent series inductance advantage over through-hole aluminum polymers, and SP caps are a type of aluminum polymer capacitor. The 3-terminal variant has even less equivalent series inductance. These are basically comparable to some types of multilayer ceramics. Well, to larger multilayer ceramics. It's not really types, but like 0805, and like these are just straight up better than like a 1206 multilayer ceramic. So these are absolutely amazing for output filtering, especially on GPUs. On motherboards, I'm not sure that, like, the thing with motherboards is that CPUs are just not as hard on the power delivery as GPUs are. So I often feel like motherboards that use a 3-terminal SP caps, they are kind of wasted. But yeah, I would not be surprised if this ITX Strix board ended up being one of the best AM5 motherboards in terms of voltage regulation. And a good chunk of that is going to just be the fact that it uses these, 3-terminal SP caps. And there's a lot of them, 8 in total. So yeah, this is one of the things that I got most excited about when I first unboxed the board, was just like, oh man, like it's an ITX, so I was already expecting SP caps. I was not expecting the 3-terminal variant. And also, like, you can see that for the other less important or like less intense power rails or less noisy power rails, ASUS opted to use the regular 2-terminal ones, right? Like, these have the little nubbins on the side. This one doesn't. That's for VDD MISC. These two for the SoC, those are regular 2 terminals as well. So yeah, I'm a big fan of what they did with the vCore filtering on here. Also, behind the CPU socket, we have some tantalums mixed in. These are 220 microfarad. I suspect they are from Vishay, but I'm not 100% certain. And they're 2.5 volts. And then this one is for SoC. So that one's like makes up part of the output filtering with those over there. And then, of course, on the front of the board, the SoC VRM has some more tantalums over here. And then we have another SP cap for VDD MISC. And again, this one's just 2 terminals, not 3. So, yeah, while I may not be the biggest fan of the power stage choices ASUS has made with this board, I love the capacitor selection. Like, especially those 3-terminal SP caps. I'm just massive fan of those. Because, yeah, like, they're just so good at output filtering because of that extremely low equivalent series inductance. So when you get fast transients, those just absorb them really, really well compared to, well, through-hole capacitors. So anyway, let's move on to the VDDIO regulator, which is just one chip. Actually, I should probably do it like this. So that's VDDIO. So this powers the PHY of the CPU. So this is a very low power rail. And this uses a Monolithic Power Systems MP8633. This is a 12 amp integrated buck converter. And then for output filtering for that, we've got some 330 microfarad tantalum polymers. Again, I suspect from Vishay, but these are, and also these are 2.5 volts. I mixed them up with these. These are 6.3 because this runs off of 5 volts coming in, so these are 6.3 volts. Yeah, this is just 2.5 volts. You can tell because there's a little E on it. That's also how you can tell these. See, little E. And also the SP caps, little E. Actually, I should say lowercase e. That is actually significant because there's an uppercase E and that's a different voltage rating. Anyway, so yeah, we have one on the front and then the other one is on the back here, and apparently a third one was not necessary. which I find kind of interesting because some of the ATX motherboards which use through-hole polymers for VDDIO will have just absolutely massive amounts of capacitance. Then again, they also usually use a rich tech, like really budget voltage controller with some basic discrete MOSFETs. So, yeah, I guess this this monolithic power systems regulator just doesn't need that much bulk capacitance, though I haven't ever bothered to check the voltage regulation on VDDIO. I guess because of this board, I might actually do that, because I do kind of wonder, like, you know, is 600 microfarads of tantalum polymers with an MP8633 better? I'm actually going to guess it's probably about equivalent, because ultimately there's a lot of ways to kind of end up in this with the same end result, especially if, you know, at some point you just hit the limits of what you can realistically do with a switching regulator, and past a certain point it also just doesn't matter, right? Like if your VDDIO has, I don't know, 20 millivolts peak to peak on it, making it 15 millivolts peak to peak is actually just not going to affect the overclocking in any way, shape, or form. Right? So, yeah, but they do kind of like, so I would guess this probably is equivalent to what you get on the ATX boards, which have significantly more bulk capacitance for VDDIO. So yeah, that's our VDDIO. Oh, one thing I forgot to mention is that for all of the inductors making up the like main CPU power delivery, ASUS is using 300 nanohenry inductors, and that brings up another interesting sort of thing to keep in mind. Like these might be 110 amp smart power stages. These inductors at 300 nanohenries are not going to do anything near 110 amps. In this size, you can technically get like 60, 70 amp inductors, but they're usually like 150 nanohenries. And the thing with inductors is that they're basically a coil of wire, though the low inductance ones are more like a strip of wire through a core material. But the thing is, like, so the more inductance you have, the more length of wire there is in the inductor, and consequently, the more DC resistance it has, right? So if you want a high inductance, high current inductor, it has to be physically huge. These are tiny. These are well, okay, they're not tiny, right? Like this is a tiny inductor. But in like, by motherboard inductor size standards, these are pretty small. And in this package size for 70 amps, I really would expect something like a 150 nanohenries or less even. So that's another thing to keep in mind is like, yeah, the power stages might have an insane nominal current rating. These inductors definitely don't. But anyway, and that's not a problem because like you're not going to be putting that much current through this VRM anyway. It's just like my point is that it's so silly that you have this like insane nominal current rating on smart power stages that you're just never going to use. So yeah, so that's the power delivery stuff. Let's talk about the memory. So obviously this is an ITX board and therefore it is a 1 DIMM per channel. And ITX boards, you know, can either be really good at memory overclocking because they have a 1 DIMM per channel memory topology and therefore they don't have to deal with the reflections of the unpopulated memory slots, or they're really bad because there wasn't enough space for a proper memory topology. Luckily, this board goes into the very good category. So far, this has been my favorite motherboard out of the X870s I've tested for memory overclocking, other than the clear CMOS button. But yeah, as far as actual like memory overclocking performance goes, this thing is really good. And one neat thing that ASUS is doing with this board, though I don't know how impactful it is that they're back drilling the memory vias. So what you'll notice if you look at the memory vias, so this is the memory slot far away from the CPU socket. This is the memory slot closer to the CPU socket. The CPU socket is over in that direction. You'll notice how like we have like regular looking vias over here, and these have very big holes in them. Right? And it's not every single via, but basically this is done on signal vias. And the thing that they're basically doing is when you have a multi-layer PCB and you're trying to run a signal from an internal layer up to a top layer, which is what you're doing, right? Because the memory slots are SMT, so they're surface mount. So you basically have a pad onto which the like memory slot pins. That's not a very good pin. I don't know what a memory. I give up. I don't actually know what. I think they might be like this. Anyway, so memory pins are SMT devices, right? So we want to go from like an internal layer of the motherboard, because again, if you look at the back of the board, right, you can't see any memory traces back here because there's all this random stuff. I actually, like, I don't know what all of these do. It's just like a bunch of MOSFETs. I think they're for like power sequencing. We have what I'm guessing is a linear regulator of some kind. But anyway, so we don't have any actual data traces back here. And even then, for DDR5, you generally avoid running your data lines on the top layers of the board. Yeah, so you'll have your, data line that's internal to the actual motherboard. And then when you want to run it up to the top layer, you basically need to make a via that goes all the way to the very bottom layer. Now, the problem with this is that you have all this extra length down here. And when you have very high-speed signals traveling through this, right, like this is to the CPU. So I'm going to... So when you have a signal traveling from the memory stick, it basically, like some of that signal goes that way, some of it goes down the excess via length and then bounces off of it and wreaks havoc on the rest of the signal. And same thing with signals coming in from the CPU, right? It hits the junction here. Some of it goes down, some of it goes up. This ends up reflecting, and it makes a mess of the signal as well. And when I say it makes a mess, it's not a huge mess. The reflection isn't going to be... well, I'm actually not sure how much of a mess the reflection makes, but this is a problem for high-speed signaling. So the workaround for this is that when they manufacture the PCB, after it's been assembled, well, after the PCB is manufactured, but before the board is assembled, they go in with a drill and they basically drill all of this out. And that's how you end up with a bunch of vias that have significantly bigger holes than the other ones, right? So these are back drilled, the ones that I've circled, and all of the like not massively blown out ones are not drilled out. And this is a very common thing for GPUs these days because GDDR just runs at insane data rates, so the reflections are a huge problem. But now we're starting to see this also more on motherboards. ASUS is doing this on a bunch of their AM5 boards. On this board, interestingly enough, they only seem to be doing it for the inside memory channel, right? Like you'll notice that there's basically no back drilling on this memory slot, but this memory slot looks like every single data line is getting back drilled. So, which makes sense. But it makes sense that they're back drilling all of them for that memory slot, but the fact that they're only doing it for one of the channels, my theory is that basically with DDR5, it's pretty typical that the outside memory channel is just better than the inside one. I'm not really sure why that is, but that's just a general thing that I've noticed with DDR5 motherboards is that the outside memory slot is always the best one. So I'm guessing the reason that they're only back drilling the inside one on this board is that back drilling the outside one wouldn't have any purpose, right? Because if the inside one is struggling to hit, say, DDR5 8200, and the outside one is doing 8600, back drilling the outside one so that the outside one does 9000 doesn't help your inside one do 80, like isn't useful because the inside one is still gonna, even after back drilling the inside one, the board is still gonna overall top out at like 8600 with 2 memory sticks. So, yeah, that's an interesting little extra that ASUS is doing. I don't know how effective it actually is for this board, because you'd have to basically test a version of this board without the back drilling, and yeah, there's no way I'm doing that. Yeah, an interesting like extra that they're doing with the memory topology. And also, funnily enough, on some of the ATX boards, they actually do it for all of the vias, for both of the channels, not just the inside one. which I find an interesting difference with this board compared to, say, the ATX boards. So, yeah, though this thing has so far, like the ITX has for me so far been the best memory overclocker, which again, it's a 1 DIMM per channel. So assuming that the memory topology is good, which it is, it's like basically guaranteed to be better than a 4 DIMM motherboard. Which again makes me even saltier about the fact that the clear CMOS button is like not implemented properly. But anyway, so that is the X870i, Strix X870i gaming Wi-Fi. It's very expensive for what it is. The clear CMOS button is a disappointment. Well, is it? Well, yeah, like it is really expensive for an ITX board. Then again, like ITX boards have a premium because they are really cramped. I like the VRM. I like the memory I like the memory overclocking. And yeah, that's basically my thoughts on this board. So, hopefully you found this somewhat interesting, if not particularly useful. And that's it for the video. So thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon and like a spring store where there's like shirts and hoodies and other merch. And yeah, and there's like a bunch of links in the description that you could check out if you want to support the channel. That would be much appreciated. And yeah, that's it for the video. So thank you for watching and goodbye.